In problem 1, we will explore how class can help us in numerical integration and compare the class and traditional approach. We have learned many skills on integration, such as integration by part, substitution, but we all know that this kind of method are limited. There are always some integral that can be evaluated in traditional way, just like the example in the slide. Therefore, numerical integration is what we need. Numerical integration can only approximate their integrals. The area of numerical integration is called error bands. Even the error bands is very tiny, it must exist. In MATH1014, we have learned several numerical integration methods, which is midpoint rule, trapezoidal rule, and Simpson rule. In the next slide, we will take them as an example. Now you can see the sample question. F of x is equal to e times 2 cosine x, and I is equal to the integral of fx from 0 to 2 pi. In part A to D, it's asking for approximating I by Simpson rule, which is called S sub n, and also approximate it by midpoint rule, which is called M sub n, and represent the number of subintegral. It also requires us to find out the upper bounds of the error. In part E, it requires us to use class to approximate the value of I. In part F, we are going to find out what of the approximation method is better. In part G, we are going to find out what the number of subintegral n is if we want the error within 0.0001. Here is the formula of midpoint rule and Simpson rule. M sub n is equal to b minus a over n times the sum of f of x sub k minus 1 plus x sub k over 2. S sub n is equal to b minus a over 3n times f of a plus 4 times of f of x sub 1 plus 2 times of f of x sub 2 and up to f of x. The error bands for midpoint rule is represented by e sub m. The absolute value of e sub m is less than or equal to k times b minus a cube over 24n squared, where k is more than or equal to f double prime of x in the range of integration. The error bounds of Simpson rule e sub s is less than or equal to k times b minus a to the fifth over 180n to the fourth, where k is more than or equal to the fourth derivative of x. When we use traditional approach to solve this problem, we have to substitute the corresponding x to fx for several times. In this case, we find out what the tan subintegral is and substitute them into f of x and use the formula we mentioned above to evaluate it. In part B, the question has already told us what the k is, so we just have to substitute the value into the equation. But what if the question doesn't imply the value of k? We will explore how to get its value from class later. In part C and D, it's similar to what we did in part A and B, substituting the corresponding value into the formula. In part E, we will do it in class. In part G, we know that the error bounds is less than or equal to 0.0001, and we set up the inequality, then we can solve it.
Now, let us talk about how a computer algebra system can be used for understanding of numerical integration. As mentioned previously, error bounds in integration have a constant that needs to be computed, k. For this question, the k value has already been given. Most of the time, we are required to obtain this k value by ourselves when computing the error bounds of integration. Obtaining the derivatives, especially doing it 4 times for Simpson's rule, will be tedious. As such, we can use CAS to obtain the first 4 derivatives of the function, making our lives drastically easier. Here, we compute the first 4 derivatives for the question and store it in a variable. We will be using the second derivative function to compute the midpoint rule error bound and use the fourth derivative function to compute the Simpson's rule error bound. To obtain this fact, we can use CAS to show the second derivative function. Note that the interval we use is from 0 to 2 pi. Now, from that, we see if the greatest y magnitude is in the maximum or minimum. As we can see here, it is from the minimum, and we can use CAS to obtain this minimum value. The value is negative 2.718, which is about the value of negative e. Don't worry if it's negative, because we are going to use its absolute value, and we obtain K value, which is e, consistent to the given fact. For this, we are doing the same thing, but in this case, we are using the fourth derivative function. From the interval of 0 to 2 pi, now we can see that the greatest y magnitude lies on the maximum. Using CAS, we can analyze the maximum, which is obtained as 10.873, roughly the value of 4e and consistent to the given fact. We will also be using CAS as a graphical calculator tool to obtain the integral given in the question, which is the integral of e to the power of cos x from 0 to 2 pi. Now, we obtain the value of 7.954927 to 6 decimal places. So now this will conclude the end of our first problem.